Hello and welcome to my talk. Today I want to share with you Moulin Coding, which is a multilinear algebraic solution for cloud storage services. First of all, I will cover some motivation from cloud storage services. And then I will show you the construction of Moulin Code for a special case. And finally, I'll briefly mention the construction of Moulin Code for the general case. So here is the motivation. A cloud storage service is a collection of hard disks that help you store big files. Initially, you upload the big file to the cloud. Each hard disk will store part of the file. You then delete the local copy to free up some space. Later, when the file is needed, you download the file from the cloud. The cloud company guarantees that it is exactly the same file as previously uploaded. From your point of view, it just works smoothly, but the cloud sees it differently. So what could go wrong behind the scene? Well, the first difficulty is that errors, mostly erasures, occur spontaneously. To ensure that errors do not corrupt your file, the cloud is equipped with error-correcting code. For instance, we may use a 753 MDS code to protect the file, meaning that every set of 5 disks contains sufficient information to recover the file. Here's another example figure, and here's the third one. The other difficulty is that fixing errors costs money. Certainly, we can recover the file from healthy disk and simulate the user uploading phase, but we want it to be cheaper. Here is the example figure, and here's the third one. So here are some notations and requirements of being a good cloud that are used in literature. The file consists of m symbols, and there are n hard disks. Every disk stores alpha symbols. So here, alpha is called the disk capacity. The first requirement is that every set of k disks suffices to recover the file. The second requirement is that every set of d disks can reconstruct from scratch one other disk by each sending out beta symbols of what it has. And here, beta is called the repair bandwidth. So now, designing the cloud becomes a linear coding problem. We can formalize what a cloud should satisfy. The file size being m symbols means that the file is a linear map phi from fm to f for some finite field f. The fact that there are n disks and each has capacity alpha means that the h disk store the restriction of phi to xh, where xh is an alpha dimensional subspace. The fact that any k disks recover the file means that for any k subspaces xh1 xhk, they span the domain of phi. The fact that any d disk repair with bandwidth beta means that there are subspaces yhf that are beta dimensional and such that yh1f plus plus yhdf contains xf. One such tuple, nkd alpha beta m xh yhf, is called the regenerating code. It is regenerating in the sense that the disk can regenerate erased disk. Sanity check. Usually we have k less than or equal to d and d less than n, which means that repairing is possible. And usually we have d beta less than m, which means repairing is non-trivial. We are not reconstructing the whole file while we repair. So now I can go over the construction of Moulin Code for the special case, where d equals k. Let W be Fk, and we consider the following wedge multiplication map that maps x tensor y wedge z to x wedge y wedge z. It has a natural transpose map called the co-wedge multiplication that maps x wedge y wedge z to x tensor the other two minus y tensor the other two plus z tensor the other two. We now let the file be any map phi from W tensor W wedge W to F such that the restriction of phi to the image of nabla is 0, where nabla is this map, meaning that phi satisfies the following parity check equations. 0 equals phi of nabla of x wedge y wedge z. By linearity, this is equal to the evaluation of phi at x tensor the other 2 minus phi at y tensor the other 2 plus phi at z tensor the other 2. Next, we let the n disks choose vectors C1, C2, Cn such that they are MDS, meaning any k of them span W. We then let the H disk store the restriction of phi to CH tensor W wedge W. Now we can verify why any k disk recover phi. Let calligraphy k be a set of k indices. Then the summation of CH tensor W wedge W over H in K is equal to the span of CH over H in K tensor W wedge W by linearity. This then equals to W tensor W wedge W by the MDS property. But the later term is just the entire domain of phi. Once we learn the restriction of phi to its entire domain, it's equivalent to learning phi. So that finished the proof. Okay, so now we assume that the F disk is erased and we want to reconstruct. To do that, the H disk will send it the restriction of phi to CH tensor CF wedge W, where the the W here is replaced by CF. We now let D be a set of D indices. Then the summation of CH tensor CF wedge W is equal to the span of CH over H in D tensor CF wedge W, which is equal to W tensor CF wedge W. So now we can learn the evaluation of phi at CF tensor Y wedge Z, where Y and Z are arbitrary vectors, because we have the parity check equations. We know that this evaluation is equal to phi evaluated at Y tensor the other 2 minus phi of Z tensor the other 2. And the right hand side is in the W tensor CF wedge W, so we know those values. This finished the proof that we can repair the erased disk by sending these messages to it. So that's the end of the k equals d construction. I'll now briefly mention the construction for general case. Let V be f of d minus k. Notice that when they are equal, this space just vanishes. We then let U be V direct sum W, which is isomorphic to Fd. And now we consider the following diagram that has W wedge W wedge W, and by a nabla map, we can separate a W. This W embeds into U, and the co-kernel is V. Now we have W wedge W, and by a nabla map, we can separate another W. This W embeds into U, and the co-kernel is V. We have one less W. We use a nabla map to identify this space with this space. This W embeds into U, and the co-kernel is V. We will not let the map phi be any map from the direct sum of U spaces, that is, any space with U in it, this one, and this one, to F. That vanishes on the image of identity minus nabla. So this means that we have 4 parity check equations. For example, the first one is 5 of x wedge y wedge z equals 5 of x tensor the other 2 minus 5 of y tensor the other 2 minus, you know the rest. The second parity check equation corresponds to the second nabla map that says 5 of x tensor y wedge z equals 5 of x tensor y tensor z minus 5 of x tensor z tensor y. And then there's a third parity check equation that seemingly does nothing, but it's in fact a gluing of subspaces. And then there's a hidden fourth nabla map, and it says that phi of x tensor y tensor z equals 0 because nabla goes to nowhere. So similar to before, we will let n disks choose vectors a1, a2, an from U such that they are MDS in the following two sense. First, every D of them span U, and second, every K of them span U quotient by W after the projection. We will now let the H disk store the restriction phi to AH tensor W which W plus V tensor AH tensor W plus V tensor AH, which means that we will replace every occurrence of U by AH. So we can verify that any DK disks recover the file. Let the calligraphic K be K indices, and let X be the span of AH for H in K. By the MDS property, we have that V plus X equals U. And now we start learning the restriction of phi. We first learn the restriction of phi to this subspace by the parity check equation, and then the restriction of phi to this subspace by downloading the disk, to this subspace by the MDS property, to this subspace by projecting, to this subspace by the parity check equation, to this by downloading, this by MDS, this by projecting, this by parity check equation, this by downloading, and finally this by the MDS property. So now we learn the evaluation of phi at all possible U subspaces, which means that we learn the phi itself. So this finished the proof that any K disks recover the file. For repairing, we have another map called nabla. We will let the healthy disk send the restriction of phi to the image of nabla, where nabla is this weird definition that I'm not going to speak out. The weird definition is to satisfy the two following properties. The first is that the definition extends to tensors of arbitrary length, and then it becomes a differential operator, aka a co-boundary operator, and it is linear in AF. The second property is that if we have tensors nu and omega, then phi of partial of nu tensor omega minus phi of nu of nabla of, phi of partial of nabla of nu tensor omega is equal to plus or minus phi of nu tensor AF tensor omega. The left hand side is the evaluation of phi of some vectors in the image of partial. The right hand side is the erased content. So now we can verify that we can repair a erased disk by sending this type of message. So that's the general construction. And for even more general parameters, we have a larger diagram that starts from 4 W's wedging together and ends with 4 V's tensoring together. For even larger diagram, we also have the following building blocks that looks like this. And then we have a more general nabla that sends this wedge to these tensors. And then we have a general version of partial. Okay, so now comes to the true question. What's the performance of our regenerating codes? Well, here are some reductions for the ease of comparison. Usually NKD depends on the actual applications, so the papers on this subject will fix NKD and compare different codes alpha, beta, m. The researchers usually start from n equals d plus 1 and increase n later, so it makes sense to ignore n and parameterize the comparison by k and d only. It is also common to assume that the file is very, very large, so m can be pretty large and we only care about the long-term efficiency, which in some sense is the homogeneous capacity and the homogeneous bandwidth. In short, it is reasonable to plot all possible alpha over m and beta over m, which is the homogeneous alpha and beta, for each and every KD pair. So here's the plot, assuming K and D equals 5 and 6, which is the example given in the beginning of the presentation. The plot shows the achievable quotients. The number in the square bracket is the width of the diagram. The one I show you is width 3. After this work, we have 2 open questions left. First, is Moulin Code's construction isomorphic to any well-known structure? The second open question is, are Moulin Codes optimal in terms of the homogeneous alpha and beta plots? And that's the end. Thank you for your attention, and now I can take questions.